Today I'm joined by James Douma. He is a machine learning expert, a Tesla investor, and he's been on my channel several times to help us kind of unpack and understand Tesla FSD. And in this episode, we've got a special treat for you guys. We're going to start to go deep into the weeds and try to uncover some of the architecture, some of the approach of Tesla SFD. But first, I want to welcome you, James, to the channel again.
Thanks. I'm glad to be here.
Yeah.
This will be interesting.
Yeah, it's been fun. Every episode, I gain a lot of kind of understanding, and I think it's a huge value add to myself and to others of you having been here. Okay, great. So today we wanted to, James and I were talking, we wanted to go over Andrej Karpathy's talk at Scaled ML. This was back in February of 2020. And James and I have been talking about this talk as one of the most significant recent talks that Karpathy has given, describing the architecture of Tesla's FSD, how we can understand it, where they're headed. So we wanted to kind of go into some of the technical stuff. And this will be kind of a learning session for myself mostly. I'll ask questions and kind of, try to clarify things. And James will try to go step by step, uncovering the architecture kind of Tesla's latest developments. First, I want to ask though, with this talk and I'll link the talk in the video description below. What stuck out? Like, why is this talk significant in your opinion?
Well, probably the best thing is it's recent. Karpathy's done other talks in the past that had similar levels of detail, but of course, Autopilot was at earlier level, points in its development then. So this is the most recent talk that he's done that has a decent amount of detail in it, and so that's why, if what you are interested in understanding is like what's FSD beta, how is it different from what AP was before the non-FSD version, and where's it going, what have they changed, then this is like a good reference for that.
And then you've also said that you were able to look at some of the code recently, right, of the neural nets. Did the code that you looked into from Tesla's full self-driving code, did that match up with some of the stuff that Karpathy was talking about in his talk?
Yeah, generally. I'm not really looking at code so much. I'm looking at the architecture of the neural networks. Like we sort of figured out a way to figure out what the architecture of the neural networks not all the neural networks, some of the neural networks, the really big ones, are in the car. That was, it's also possible to look at the code. It's a lot harder to interpret what's going on in the code. And like that's a pretty significant undertaking. Whereas, at least, for me, having looked at a bunch of these things, just looking at the shape of the neural network is kind of a fingerprint. You look at the shape of the neural network and it gives you a pretty good idea of what they're trying to do with this neural network, because different neural networks have different objectives. They have different shapes. So it tells, and then we can see, because we've got a few different snapshots. We saw the neural networks a couple of years ago. We saw them a year ago. And so we can sort of look at the evolution and get an idea about, what's working for Tesla, what's not, what they're experimenting with, things like that.
Mm-hmm. Awesome. So in Karpathy's talk, he talked about, I guess, pseudo lidar, kind of image depth mapping, and kind of the overall architecture of Tesla full self-driving. Where would you like to start off kind of diving into?
Well, yeah, so I went through it a couple of different times. The talk, Karpathy in the talk, he spends about the first half of it just doing kind of a general introduction to what Tesla is doing, like their development approach. For an audience, the audience for this talk is people who know a lot about machine learning and who don't know very much about Tesla. So the first half, he basically explains Tesla, and I assume your audience probably knows that part, so I thought I'd skip it. And then about halfway through, he starts talking and showing some examples of internal stuff that they're working on that is recent developments in what they're doing. And in particular, I wanted to talk about things that I thought were relevant to maybe people's experience and helping people understand what the neural networks in AP are trying to do in particular. So I thought I'd just go through it in order.
Let's go for it.
I had a couple of points here. Let's see, is the screen share on
I'll go
now?
ahead and switch over to screen sharing mode here.
Okay, so let's start with Backbone here a minute. I have that. Okay, so first, this is, I'll pull this up a little bit. So this is a slide that sort of it shows one camera, and it conveys this idea that a camera in the car, it takes an image. That image gets a little bit of pre-processing, and then it feeds through what I call the camera nets, and what Karpathy here is describing as a backbone. And so this is basically a big neural network that just basically takes all these pixels, it processes them, looking at relationships between the pixels according to the way that it's been trained, and then it squirts out a number of outputs. Now he has 3 examples here. He shows moving objects, and if we zoom in here, you can see, whoops, wow, that overreacted a little. Okay, so like in this frame, he's, it's showing a box around a car, and then road lines, and in this image, it's highlighting the lines in the center of this, the road markings, and then here road edges, and then this image kind of shows that the output. This output is the frame marked up showing where, say, this curb is here on the edge. So this is kind of a couple of examples of outputs that a single backbone network on a single camera might put out. In the networks that are actually in the cars, we see anywhere from dozens to maybe 100 of these outputs, depending on the camera. Obviously, the front cameras, side cameras, they don't all look for exactly the same kind of thing. They look for generally similar kinds of things. So that was an interesting
And how many cameras? Is it 8 cameras that Tesla?
Yeah, so there's 8.
Okay.
Most of the driving is done with 7 of the cameras. So on the front of the car, there are 3 cameras that basically look straight ahead. There's a fisheye, which can see, it's got almost 180-degree field of view. Then there's what's called the main camera, which has about the field of view that it's about a 90-degree field of view. It's a very recognizable field of view. And then they have one called narrow, which is kind of like a telephoto view. It's looking well down the road. So narrow is interested in things that are a couple hundred feet down the road. Main is interested in stuff that's close to the car, within a couple of vehicle lengths. And then fisheye basically pulls in things from the side too. So like if you're sitting in an intersection, fisheye can also show you a certain amount to the left and the right, with, things that as a human you'd have to turn your head to see. So then there's 4 cameras on the sides of the car. There's 2 in the pillars that basically look to the side and forward. Now the pillar is it's the B pillar, which is it's the separation between the front door and the back door. There's a camera embedded in that black band. Then there's a set of repeater cameras, which repeater is it's like a little turn signal indicator that's actually on the front fender of the car on the side of it. So the Teslas, they have a camera that looks backwards from each side of the car there. Now additionally, so that's 7 cameras, 3 to the front and then 2 on each side. There's another camera which sits above the license plate. And, when you back up your car, it's the camera that shows you the rear view. So the neural networks, they're also capable of using that. You don't tend to see it used in a lot of the neural networks. For instance, the bird's eye views, they're totally dominated by the other 7 cameras.
Okay. Have you noticed over time Tesla incorporating more of the camera data views into their neural nets? Yeah,
certainly. Like some years ago, they were using like 2 of the front cameras for a really long time in early versions of autopilot. And then they started incorporating the pillars, and then the repeaters came in around the time that nav on autopilot, where it could start doing lane changes on its own. Then it was really using all the cameras for the first time, really integrating everything. And then since then, they've always done a lot of processing on the front cameras. I mean, those are obviously really important to being able to drive the car, but the amount of work that they do on the side cameras has increased a lot over the last 24 months or so. And so now all the cameras basically have really big networks, and they're all doing a lot of processing. But of course, there's 3 cameras to the front of the car. And some of the front cameras actually have more than one backbone. They have multiple backbones that are specialized on different kinds of subsets. I mean, in this example, Karpathy shows like moving objects, road lines, and road edges. It's in the most recent version of the networks I saw. They actually have completely different backbones for these big categories of objects. Like they have a separate one for moving objects and a separate one for static stuff on the road and so on.
Have you noticed, like with the separate cameras? I mean, is this more of a hardware 3 a kind of thing where the old hardware, it just probably couldn't process fast enough all of the camera data? Or did you see in the old hardware also use of all of the cameras?
So Nav on Autopilot was deployed before Hardware 3 came out.
Mm-hmm.
And is this right? I think that's right. They're probably pretty close together in time, but Nav on Autopilot actually works fine on the Hardware 2.5 and Hardware 2 versions of the car. The amount of stuff that I see in the FSD networks is way out. It's 20 times too big to run on the Hardware 2.5 processor. So they're definitely not running that on Hardware 2.5. But all of the functions that I saw in networks up until I started seeing FSD networks, it seemed like it was being scaled so that it could fit in Hardware 2.5.
Okay, cool. Yeah, why don't you go ahead and continue on with yeah.
Okay, so now Karpathy in this talk, he uses this slide as kind of an introduction to talking about. He kind of leads up to an explanation of the bird's eye networks and how using a neural network to develop this bird's eye view. And just to recap, the bird's eye view is Tesla has recently gone to asking the car to give it a map of everything, asking a neural network to generate a map of everything that's around the car in kind of one field. And previously, they would have sort of perspective views where, they would, for each camera, you would imagine an image sort of as we had in these images where you'd like, show me where the cars are. And it would show you in the camera's field of view, like here's a car, here's a car, here's a car, by putting boxes around those. The bird's eye view, it asks the network to take a step back, imagine you were looking at the car from 100 feet up or 200 feet up, and imagine all the area around the car. And then asking the network, tell me where the cars and the pedestrians and the road lines and the curbs are in this view. So one of the first places that this became really valuable to Tesla and a really good test bed for this is Summon. So, they have this advanced Summon feature where you can call the car to come to you from across a parking lot. And advanced Summon is challenging in ways that driving the car isn't, which are particularly amenable to this bird's eye view being helpful. And one of those things is that, in parking lots, it's often really hard to tell where the car is supposed to drive. They're not nearly as well delineated as driving on roads are. So, and the curbs can be in all of these really complicated patterns. And so one of the things they wanted to do with Summon was basically have the neural network tell me where is it safe to drive in the parking lot. And so he's talking in this section about how they tackled that problem. And originally, they had tackled that problem just with geometry, which is basically, you have a camera and it's a projection onto the world, and you can use trigonometry to say, well, if I see the curb at this point in the picture, it must be at this position relative to the car in the real world. And they were using that to try to estimate where the boundaries of where it was safe to drive was. And they were getting that works pretty well when you're really close to the car, because there's a lot of difference looking, if you look out the side of the car, it's pretty easy to tell when something is like 5 feet from the car versus 10 feet from the car. But when you're looking 40 feet from the car and you're trying to tell if something is 40 versus 45 feet away, that's a lot harder to do. And it turned out they discovered when they were developing the 7 that they actually needed to understand that distance, and the geometric approach wasn't doing it for them. When they switched using a neural network for this BEV approach, they suddenly started getting much better results. And actually, one of the most impressive slides in this whole talk, which I'll show you a little bit later, is where Karpathy shows, so this is what the ground truth is. In other words, this is what it would actually look like on a map. And then here's what the geometric thing was showing us, and it looks terrible. And then here's what the bird's eye neural net was telling us, and it's perfect. It's like a really good match to the map. So you can see there what a leap forward it was for them to step away from this geometric approach to understanding the environment, and essentially having a neural network take a bunch of camera views and try to show what the world looks like.
Do you think they actually, like when they were doing, let's say, Smart Summon, was the expectation that a geometry approach would actually work? And then as they hit limitations, they're just like trying to pivot, trying to explore other solutions with neural nets. And so was this kind of like on the fly, you think, kind of adaptations where they just were trying to solve this problem and were, throwing different things at it, and then, the neural nets came out to be kind of the winner?
It's a little of both. I think their expectation is that in the long run, the neural networks will win a lot of this stuff. But in the short run, neural networks are new, and the best way to use a neural network to solve a problem can be not very obvious. And a lot of the geometric techniques are mature. They've been around for a really long time. So if they need to do something today, an approach they can take is, well, use a geometric approach to just get going. And then you start trying different things with the neural network to figure out what the right way to do it with a neural network is. And I think, generally when looking at how the different neural networks evolved over time, we do kind of see that. It's like one of my favorites is the windshield wiper thing, because every time I saw a neural network, the windshield wiper network, it had radically transformed. Like, it wasn't this arc where, they started with this and then they gradually moved in some direction. It went all over the place. They did all kinds of things trying to get the windshield wiper to work. And I think that was an example of where they didn't think it was going to be that hard when they started out. And then it turned out to be surprisingly hard. And they had a whole bunch of experiments. And then eventually they found something that worked pretty well for them. And that's what they're doing now.
Okay, cool.
So let's see. The next slide that I thought might be interesting would be getting to this. Okay, so here's where... he talks a little bit about their general design philosophy here. Okay, so now when they tried to do the neural network, how did they have to go about changing stuff that was in the car? So now what they want to do to be able to use the neural network to solve this problem, to understand the thing, is at a minimum, well, you need to rotate the view. Like each camera, you need to be able asking that camera, what would I see from above in the field of view that you've got? Then you want to put all the cameras together, because no camera can see all the way around the car. And because the cameras really overlap a lot in their fields of view, they can act as a check on each other in their overlapping parts. And if they do it, because each camera wants to see a consistent view and its edge has to be consistent with the adjacent camera, the cameras all together end up being a good consistency check for all of them. So essentially, when you try to put them all together and make it make sense, the accuracy of everything gets a lot better. So then another thing that you can do once you've integrated all the cameras into a scene is you can say, well, it should also make sense across time. There's continuity between what I saw a second ago and what I see now and what I will see a second from now. So another kind of consistency check that all these things can do is, say I do my top-down bird's eye view, and now what I want to do is I want to stitch, several seconds of those together and ask them to cross-check each other, and then my accuracy goes up again. And this is what you see them doing here in the network. So here we have them. They've got, he's just got an example of 5 cameras here, 1 from the front and 4 on the sides. And then this is what we were looking at before, that was the backbone. Now this time, the backbone isn't making these outputs down here directly. Instead, what the backbone is doing is it's extracting all these features and it's feeding them into another neural network that takes the output from the individual camera networks, and it makes a unified view. It combines all of them together. The next stage is the temporal one, where you look at several over time, like maybe 8 frames. So you take the last 8 synthesized views that you have, and you ask them to all be consistent. So you have a network that cross-checks all of those against each other. And of course, one side effect you get of time is now you can see moving objects. If you see a car moving from frame to frame to frame, one of the things that this network can output is it can not just tell you there's a car there, but it can tell you what direction it's moving and how fast it's moving. So then the last thing you do is you ask it to rotate the view, so that you're looking down on the car. Now that you've integrated all this stuff together, both across space and across time, now we rotate the view. And then in the rotated view, now we ask it all the things we were asking it before. Where are the pedestrians? Where are the road signs? Where are the road markings, curbs, and so forth? Now, in the rest of these examples, Karpathy is just using curbs in the summon as kind of an example for what they're doing. But of course, you would tend to see these benefits across all the different kinds of things that they were trying to do.
Mm-hmm. So a quick question here. So I'm wondering, this whole fusion of the different cameras into kind of a bird's eye view, is this something you think that Tesla has pioneered with, or is this something that is kind of growing more common with, vision and neural nets?
So
have you seen this?
Academics have been trying to do this for a little while. Just in the last couple of years, there've been several interesting papers out on bird's eye view networks. My experience with like looking at Tesla's networks is I'll often look at the networks and I'll see some stuff going on, and then I'll go to the literature and I'll search for other people doing this, and I will frequently find that somebody just came out with a seminal paper on this topic like 6 months or a year before Tesla did it. So I think they probably are innovating, and they're certainly adapting these ideas. Typically, what you see the research having been done on is not exactly what Tesla wants to do, but it'll be very, very similar. And then, and my guess is that this inspires Tesla to try something along those lines, and then they figure out how to adapt it to what they're trying to do.
Interesting. And then I'm also curious, so you've got this fusion bird eye view, and then it seems like Karpathy is saying that they're relying on this bird's eye view increasingly more over time to drive. How do you think they're managing these two views? Meaning you have the old kind of forward-facing view, right? Then you have this newer kind of bird's eye view. Like, when do you rely on the bird's eye view versus when do you rely on the old, let's say, forward-facing view? Is there some type of, you think, switching going on, or do they have to match up, or how does the logic work with that?
Well, so it's, Autopilot's a product that's in development. It has an arc, and each time, they do lots and lots of small revisions that they push out to the fleet. And for the most part, what they do is they introduce new functionality, and then they gradually refine it over time. So I think we're at a point in time right now where they still have all the outputs that they got from those backbone nets that were on the original cameras. And they had a bunch of code that they developed because they didn't used to have the bird's eye stuff. So they had some relatively mature functionality that was using those capabilities. And they still have it in there. So for instance, you saw that in the original backbone thing, for instance, they have a moving objects output. Like maybe one of those would be cars. That's certainly identifying other vehicles that are on the road is a big feature that these networks develop. So they had a function that was working reasonably well for quite a while that they had developed to some level of refinement. Now they bring in the bird's eye network approach. Now the bird's eye network, it's answering the same question in a sense, but probably what you don't see is them immediately throwing away the old way of doing it and moving to the new one. Because in the beginning, the old one is going to be pretty competitive because it's fairly refined. And the new one is going to have, it's going to have some bugs and it's going to have some accuracy limitations. As you use the new one more, it's going to get better. And once it gets good enough that the old one isn't really adding value anymore, then you can drop it. And so I think a lot of features end up doing this thing where you had the version that you were doing it before, you come out with the new one, and gradually this one gets better and better and better. And eventually you're like, okay, we don't need to waste our time on this one anymore. And then it comes out. And they're simultaneously doing this with a lot of different functions at any given point in time. So, every snapshot, you see some things that have been thrown away, some things that are brand new and being tried out, and some things that are kind of in a transition in between. So I think what we're seeing right now with BEV nets is the BEV nets they're showing their success at being able to do this. And so they're doing more and more things with the BEV nets. They're adding more BEV nets and they're pulling more of the value out. I haven't yet seen them deprecate old stuff, but that would be a function of like when the BEV nets were doing it so well that you didn't need it anymore. Now there will be some things that the BEV nets won't be good at doing, like they can't tell you how tall a bridge is that you're coming up on, right? I mean, there's some things that just require that vertical, point of view, and there will be other things too. For instance, in the BEV net, you can't tell the slope of the ground. So if you're driving around a curve and the road is banked or counterbanked, like you don't see that in the BEV net. So that's something you always have to do in the camera view.
Got it. Sounds good. A BEV, so bird's eye view. So BEV.
Bird's eye view.
Got it.
Yeah,
net.
sorry.
Okay. Awesome. Yeah. Feel free to continue on.
Okay, so let's see. I think we talked about the architecture here. They have the backbones. They feed into a fusion layer. They make it make sense across time. Then they do the top-down view, the BEV view, and then now they're pulling the objects out there. So let's see. That's the BEV Net. Where are we at? 1953. Okay, so this is where Karpathy is basically showing the success of this method in the specific case of predicting where curbs in parking lots are. So we got three. So this is the ground truth. So this is, you got a map of the parking lot, which maybe you pre-mapped it, or maybe you got this from Google or something like that. This is what the geometry is telling them about where the curbs are. So you can see this is where the car is. It's this blue dot. And the stuff that's nearby, it's not too bad. It's useful. Like within 1 or 2 car lengths, you can tell what you don't want to run into. But it's not very helpful for help. It's not very good at helping you understand the shape of this intersection that you're coming to, and like what your options are for navigating it. Because as you get farther away from the car, things get closer to the horizon line, and the uncertainty in the positioning gets to be really large. And then this is the output of the neural network. And while you can see that the neural network is not a perfect representation of the ground truth, this is reality, it's got all the important features that are there. And this was a fairly early version of the BEV Net that they had developed in particular for Summon. So what I see in the FSD version of the networks that I was looking at was basically lots and lots of this getting used. I mean, they're using BEV Nets everywhere.
Got it.
Does that make sense?
Yeah. So with the BEV Net's bird eye view, so it's improving kind of how they're seeing the entire surroundings, right? Before it was, you're just looking at curbs and different things. The more accurate is, the closer objects are more accurate, but you're not able to get kind of the bigger picture. But with bird's eye view, you get the bigger picture, and that improves kind of the whole visibility, right? And the ability to make better decisions, I guess, through driving.
Yeah, that's generally true. What I wanted to try to give you here was a sense of the visceral difference in the two. Like for going back to this image, imagine, this is, if you're here in this car and you're trying to decide, okay, I want to make a left turn. What do I need to do over the next 5 seconds, right? And you look at this, it's not too tough. I need to turn wide enough to miss this curb, and I want to end up going about this way, right? If you go over to this scene and you try to answer that question, this is almost not useful, right? In other words, the level of uncertainty that you get just trying to predict these things from the camera views themselves is large enough that you just can't even make sense of the shape of the network, right? So this is the basic, what you get with that basic geometric approach. Now, you could refine this. You could keep working on the basic geometric approach, and you could get better at it by putting things in. But when they just took the problem away from geometry, and they gave it to a bird's eye network, and they told it, the constraints are like whatever one camera sees has to make sense for another camera. This space needs to be continuous and make sense. And as you move through the scene, it needs to be continuous and make sense. When you get these cameras to cross-correlate against each other and cross-correlate against time, all of a sudden your accuracy gets dramatically better. And in this case, you can see the difference is, basically this center image might not be perfect, but it's usable. Right? They went from something that was totally unusable, which they'd worked on a long time. I mean, they had some working in parking lots for a while before they went to the BEV Nets, right?
All right. So that bird's eye view in the middle, it looks like almost exactly the same as the ground truth. How much of that is based upon kind of using the BEV Net over time, so over a few seconds, versus just like, let's say, a standstill, frame? Are they able to get that type of accuracy with just a single frame, or is that because they're able to see it over a few seconds time?
Yeah, so there are kind of two components to that question. If you had a trained up network, say the car wasn't moving, right? You turn on the car, it's sitting in one spot, it looks out. What is it going to see at this intersection? So you haven't had any motion. It's probably not going to be as good as this, but it's not going to be bad. It's going to be the time component. When you're, stopped at an intersection or whatnot, you don't get to use it nearly as much for sort of orienting yourself in the world. but it does add some value. It's definitely going to make it's going to make the network more accurate. Like, when the car drives through a scene and it sees like a curb move from the distance into the foreground and slide past, that has to have a kind of consistency to it in how it moves through. It shouldn't jerk. It should kind of keep track with the motion of the car. So relying on that kind of motion consistency does allow AP to be a better judge of at any moment in time where that curb is or that object actually is. Mm-hmm. But the place that it really has a benefit is when you're training, right? Because when you train these things, as soon as you add the temporal, as soon as you start training that temporal layer, your training material has to have time in it. So this is when Elon was talking about training in 4D, right? The 3D is, including the bird's eye view, the top-down look. So we know where all these objects are in space, and we're testing against that. And the 4D is time, where we start stitching these frames together. That predicting that time dimension for the neural network is really, really hard. And so when it gets good at that, it's really good at the static frames. I don't know if that makes sense.
Mm-hmm. Yeah, definitely. So I'm also curious, like Autonomy Day in 2019, I think it was April or so of 2019. I'm not sure. Did they mention bird's eye view much at all at that presentation? Because we fast forward to February of 2020, Andrej Karpathy at Scaled ML, and he's basically saying, "Hey, this is the big thing we're building a lot of this stuff on." But on Autonomy Day, did they have that type of conviction back then, or is this something you think in between that time
they didn't talk about it at Autonomy Day for sure? So, if I don't think they talked about it. So, Elon's terminology that he uses is it's kind of all over the place. Like he has some, it's the word of the month or whatever that he's using for talking about autopilot. So because he doesn't talk about the same thing over a long period of time, it's hard to know what their internal terminology is and what the arc of features is inside. I get the impression he gets excited about some particular thing that's happening for him right now that's got great promise for the next couple of revisions, and you hear a lot about that. That the literature doesn't seem to have used this terminology much before a couple of years ago, but so they had Tesla obviously had done a significant amount of internal development of this by February of 2020. So they must have started working on it in some capacity around, mid 2019 or something like that. And it was around, mid 2018 or something that this started becoming a popular topic out there. And in fact, in 2019, you do see a bunch of papers come out. So my guess is that at Autonomy Day, they probably kind of knew generally that they wanted. I mean, one thing that you can see people talking about in autonomous, neural networks, autonomous car neural network circles, you can go way back and people knew that if you integrated time, it was going to be super valuable. They just didn't know how to do it. What's the right way to do it? And they've known for a long time that if you integrated multiple cameras together, that was going to be really valuable, because they're just things that this way the neural networks can cross-check themselves, the camera neural networks, and you have to bring all this stuff together and make it make sense. It challenges all the networks to get a lot better. And once they all get a lot better, then the unified view starts to get really good. So we've known for a long time that this needed to happen. It just wasn't clear what the right way to do it is. And the challenge is there are these brute force approaches that you can take where it's definitely got all the inputs it needs, right? And you just put a giant neural network on it and you just process it and you train everything against everything else. And, Google, did some early experiments, several years ago with just like getting a huge cloud of computers and asking them to do this really hard thing and just basically proving that certain things were possible, but they weren't practical on that scale because you need billions of hours of training or whatnot. So to make it useful in the real world, you want to figure out, like, what do I not need to look at? Like, what's essential to helping the neural network understand this thing that it needs to understand to do a good job of this, and what's not. important. And so you gradually whittle away all the things you don't have to do, and you get a neural network that's small enough and sample efficient enough. It's like, how much data does it take to train this function? It's got to be a reasonable number. And how much computation does it take? Well, that's got to be reasonable too. I mean, we can use a big data center, but we can't use 1,000 big data centers. There are limits. And some of the, it's like the trying to brute force the game of Go. It seems pretty small. It's a 19 by 19 board, but there are more Go positions than there are atoms in the universe by I forget, like dozens of orders of magnitude. Like, there are problems that don't seem very hard, but you simply can't brute force them. You have to constrain the problem a certain amount before it starts to be tractable. And so I think that was one of the problems, and it continues to be a problem with this whole getting a computer to understand that the world is 3D. Brute forcing that problem has been intractable. Google did a couple of really interesting, some guys at Google Brain did some really interesting things where they just brute forced. They made a little cartoon world. They really dumbed it down. It has spheres and cones and they wanted to train a neural network where you would show it one view of the world and you would ask it, well, what would it look like from this other angle? Where you would give it an arbitrary angle. And the amazing thing was they got it to work. I mean, it took a significant amount of computation, and it was very brute force. But they showed that the neural network will eventually figure that stuff out if the information is there. But the approach that they took, nobody tried to duplicate that in any product because it just takes too much data, and the world has to be too simple for it to work. So where's the good middle ground where it's computationally tractable? Like, it's a reasonable size neural network and a reasonable size amount of data and training time, but it works in the real world. It deals with all of the complexity of the real world. And that's been the challenge. And so it's just been in the last couple of years that people have come up with techniques where this started to produce results that were significantly better than what we could do before. And for a long time, they've been able to kind of muddle along. But, why do this super complicated technique that isn't getting you better results? And now they're doing these complicated techniques that are getting dramatically better results. And that's one of the things you see in this slide. I mean, you can see like there's a dramatic difference between what they were getting with the geometric technique that was a dominant approach before and what they're getting now. And, once again, you look at the ground truth, it's not perfect, but it's a pretty good facsimile of that. Mm-hmm. And it's a dramatic improvement over what they had before.
Yeah. I mean, it seems like, back 10 years ago or so at ImageNet, when, people proved that you could use neural nets to identify objects, better and more accurately than, human rules. That was like a huge breakthrough. But then it seems like this is a whole nother step up in terms of images that, using multiple cameras, depicting different views, over time, et cetera. It just seems like it's radically, exponentially grown, the field of vision and AI in less than a decade. It's crazy.
If you went back to 2010 and you asked anybody in the field, to place bets that 10 years later we'd be this point, nobody would have taken it. In fact, it's generally been the case. This was when the ImageNet thing happened, people were kind of shocked by it. It happened in like December of 2012, right? And nobody really expected, like, wow, this is a great breakthrough, and it was this huge leap forward in image processing. But really, nobody in the field expected that like in 2014 it would be a lot better, and 2015 would be dramatically better. Like at any year, you could ask people in the field like what they thought would be possible in a year or two, and they would have been way off. Like the field has so consistently and dramatically outperformed the conservative expectations of people in the field. It's just, it's nuts. And this is a story you hear over and over in the neural network stuff today. It's when I love the AlphaGo story because it's easy to talk about. But, AlphaGo, even the team that was working on it, they weren't sure they could win, right? They were super conservative about that thing. They were shocked when they beat a pro. And then the idea that like 6 months later they would take on this world champion and win, nobody believed that. That was just like beyond the pale. But then 6 months later, not only was AlphaGo beating the pros of the pros, it was so much better than human beings that the experts, like people who had devoted their life to playing Go. They can't even understand the games anymore. Like, it's playing at such a high level, it makes no sense. And now professional Go players, they use this as a reference. Like, they learn from it. It's their teacher, right? They play games against it. They analyze its strategies. They've looked at different trades off that it makes that are different from the way humans do it. And they're learning things about Go that this is a 3,000-year-old game. I mean, for 1,000 years at least, people have been very seriously playing Go. And they're finding out things that nobody ever imagined were true. And they're finding out things that they always thought were true, that have been bedrock theory in that thing for hundreds of years, are just wrong, right? Mm-hmm. The game, it just figures it out. So it went from, it went from this isn't possible to even be better than a human, to like so ridiculously superhuman. Like, it's hard to get your mind around just like how far it's gone. And it's not the only domain. Like Alphafold is another, great, it's another great story. Like, DeepMind has cranked out a few of them, but protein folding is a really important problem that people have been thinking about for a really long time. And, 20 years ago, when you bought your first PlayStation 4, you could get this folding at home like screensaver where you would contribute compute cycles. Because back then people thought, well, if we just had enough compute, we'd be able to predict how proteins fold. And if you can predict how proteins fold, that's a very important input to all kinds of biological and medical research. And people really wanted to crack that problem. And no matter how much compute we threw at it, we never got traction on it. So a lot of people have devoted a lot of time. A lot of very smart people have devoted their lives to trying to solve this problem. And progress has just been bit by bit by bit. It would get a tiny little bit better every year. And then, Google AlphaFold came out last year, and they got this dramatically better result than anybody had gotten. Like, it was much like the ImageNet results. Image improvements were going dunk, 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 and then ImageNet was like boom, right? And then next year was dunk, 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 and now the trend is completely different. Yeah. And that's what happened with AlphaFold. They were getting this kind of gradual improvement, and then boom, then next year, like, wow, boy, in 6 months, this group of neural network guys came into this field, and they made more progress than the field itself has made in like 10 years or something like that. And then this year, they made so much progress that they kind of considered the problem solved, right? I mean, they just popped right off the top of the chart on their next try. And, that's a story that we're seeing with neural networks, that, their ability to solve problems that we've struggled with for a really long time and to consistently get better is shocking to people inside the field. Self-driving cars is a really hard problem. Like, navigating the real world is a really hard problem. But this is what makes it tractable, right? If we didn't have these, it'd still be 20 years away, right? And now it's within reach.
Yeah, it's funny because like 2012 with ImageNet, people are trying to identify cats, in still images. Like, that's the big, thing. But fast forward less than 10 years, and now you could recognize thousands of objects, in multiple cameras fused together in a single second, just, across images. It's just mind-boggling, like, in less than a decade, how much progress has been made. To the end consumer,
10 years ago.
Yeah, to the end consumer, it's like they don't completely realize it because they don't understand what it took to get to this place. But it's to track it, it's definitely fascinating. Yeah, you're about to say something?
I was going to say 10 years ago, the problem of telling a dog from a cat, it was like one of those sort of example problems, that you'd like that in the field. Like, imagine writing a program where you can give it any picture of any dog and any picture of any cat, and it can tell you if it's a dog or a cat, And initially it doesn't sound super hard, but people who worked on it, it was just, from the human writing code, like nothing worked. Nothing worked, right? We worked on that problem for so long. And it's just like this example, right? And then ImageNet, it was like, solved problem, right? It's done. I mean, it might not be perfect now, but then it's like every single year the error rate halved. And now it's perfect, right? It's better than people. You got a picture of a dog, got a picture of a cat. You can build neural networks that are so ridiculously superhuman in their ability to solve that problem now. And it's been less than a decade since it was people wondered if it was ever going to be solvable. Like were we ever going to find a way to be able to do this? It's a radical change in the world.
Yeah. I think what's also interesting with Tesla is because they're kind of so cutting edge with vision and neural nets and with, let's say, autonomous driving, that's put them in this kind of pole position of really pushing the envelope. But then this applies to almost anything vision and movement. You know, for example, any drones or robots or whatever moving around. And people, I think generally, like when you look at a robot or a drone, you think it's mostly going to be the mechanical, how you build the drone or how you build the robot that matters the most. But a lot of it is, especially with like a drone, a lot of it is going to be how it flies, you know, or let's say a last foot delivery from the car to the front porch of a house. Like a lot of that is going to be intensely what Tesla is already doing right now with neural nets and vision and cameras, trying to navigate these complex areas. And like, who's better to do that than Tesla right now, you know? And for a competitor to catch and to, you know, outpace Tesla, they have to really build up a lot of expertise in this field. You know, if they're going to make, let's say, a better, let's say, robot or drone that navigates better than a Tesla, you know, what Tesla can do eventually. But it's interesting. Tesla, I think, is opening up possibly new opportunities that we have yet to see, or, you know, that are yet to be revealed with this whole AI and vision.
Yeah, I think in one of our first couple of conversations, I think you asked me, well, what would you apply this to? And I suggested that robots was a thing that you could do with it, because navigating, I mean, for a robot to navigate in the world, like, you know, a humanoid robot that's got to walk up and down curbs and stairs and open doors and pick up boxes and fold your clothes and all that kind of stuff. The world's pretty complicated. It's a really, really complicated place. But in general, it's a similar kind of problem to, you know, I mean, a car or a self-driving car is just a robot that drives around on streets, right? I mean, it's a robot. It's a much more constrained problem than in the real world. But it's not difficult to believe that the first, you know, really general purpose, you know, robots that we have in the world, that they'll need to take an approach similar to what Tesla is doing. And Tesla's figuring out how to do it at scale. Anyway, I think my answer to your question was like the process that they're pioneering for solving this problem, that itself is a really, really useful product, because aside from self-driving cars, there are many more products in the world you would want to be able to apply this process to than Tesla will ever have the resources to do. But, you know, you'll see people leave Tesla in 5 or 10 years off the autopilot program. This is, you know, how Silicon Valley works, or how the tech world works. Those people will spread out and they'll take this know-how of how to build a program. What does a successful program look like that solves these kinds of problems? And it'll seed many other efforts at many other organizations and other efforts inside Tesla to solve some of these long-standing sort of grand engineering challenges.
Yeah, awesome. Here's what we'll do, James. This is, I think, a great segue where let's wrap up this first episode, 257, at this point. And then what I want to do is I want to just continue right into our next episode, and let's finish off the scaled ML episode and really kind of go deeper down into kind of, I want to know how they determine depth of field and how far, you know, objects are and how significant that is to full self-driving, and just let you finish, you know, the whole, you know, commentary on the video. So why don't we wrap up this first part here, and then we'll just continue right into the second part. And for those watching, you guys can, I'll link to the second part eventually in the video description. So this will give you guys a good break at about the 1 hour mark. So we'll talk to you guys in a bit.